Now I want to talk about partial measurement, which I was not able to cover earlier, right? So what is the meaning of partial measurement? So let's recall what we do when we do a single qubit measurement, right? For a single qubit. And it has two basis states. What are they for a single qubit? A general one, psi equal to what? Alpha 0 plus beta 1, right? So the two basis states are 0 and 1. And you do measurement, right? What do you get? You have the probability of getting 0 is what? Everyone should be very familiar with this already, except him, right? Not just him. It's what? Alpha magnitude square. What's the probability of getting 1? Huh? Beta magnitude square. Yeah, very good. Okay. Now, what if I have 2 qubits? I have a 2 qubit system, right? So in that case, maybe psi can be represented as what? How many bases do we have? Basis states do we have? For what are they? 0, 0, 0, 1, 1, 0, 1, 1, right? And they have their coefficient. Let's say call it A0, 0 plus A0, 1 plus A1, 0 plus A1, 1. Okay? Nothing special, right? Now, let me just very simple. If I measure, I should add the if in front. If, oh, have I started recording? I think so. Let me make sure I've started the recording. Yeah. Right? If I measure both at the same time, okay? I measure both. That means I want to know what is the state of the first qubit and the state of the second qubit, right? What are the possible outcomes? All false. Yeah, I know this is very simple, but you need to be able to say it, okay? Uh, if measure both, all four can be possible. What are the probability? What's the probability of getting 0, 0? A00 square, right? Probability of getting, I guess you all know now, 0, 1 is A01 square, right? Probability of getting 1, 0 is A10 square, and probability of getting 1, 1 is A11 square. Is this okay? Anyone has a question? I know it's simple, but the most basic thing, you need to know the most basic thing well, right? Okay, but now what if I only measure, one of the qubit, let's say the first qubit, the possible outcome, if I only measure the first qubit? 0, 1 of what? The first qubit, right? The first qubit can be 0 or 1, right? Then it can be, when it is 0, what happened to the second qubit? If I get 0 for the first qubit, what can be the outcome for the second qubit? It can be 0 or 1. Then as the whole system, what are the possible outcomes? Thank you. It will be 0, 0, or 0, 1 if the first qubit is 0. Is this okay? I know it is very, looks very simple, right? It's just like classical thing, and indeed it is. In this superposition state, if I do a measurement on the first qubit, I don't care about the second qubit, then the whole system need to collapse to a state. But if the first qubit collapses to 0, the whole system can only collapse to either 0, 1 or 0, 0. Make sense? Or it can become 1, 0 or 1, 1 if the first qubit is measured to be 1. Is that okay? Okay. So let's say assume that first qubit collapses to 1, to let's say 0. What is the quantum state? What will happen to psi? It will become what? Say again? In math, there's no something called OR. What the state will be? Okay. It will become 0, 0 plus 0, 1. Is that okay? Okay, very good. So he said, should you still have the coefficient? Yes. But now, so I missed something, right? I should write down the coefficient. Should be A00, 00 plus A01, 01. Is that correct? Why? Why I need to add prime to the coefficient? Very good. So he is saying that previously we have A00 square plus A01 square plus A10 square plus A11 square equals to 1 because that the sum of the probability of measuring every state needs to be 1. Make sense? And now, after it collapsed, I only have this. So what do we require now if it is still a valid wave function? What do you require for the relationship between A00 and 01? The sum of the square need to be 1, right? And that's why he complained. He said this it should not be A00, but should be A00 dash certain number, right? But what is this value, right? So that come to the point of normalizing a waveform. A wave function. And the easiest way to do this is very simple. The wave function now, the psi dash is still equal to A0000 plus A0101, but then you divide the whole thing by square root of A00 square plus A01 square. Okay, the reason is very simple. This is just a number. I divided each coefficient by this. Think about that. Then now, because what is the magnitude of A00 square plus A01 square? I mean, it equals to something, right? And if I divide it by its magnitude, then what it means? Their sum must be equal to 1, right? So you can go back to chat. When you do any normalization after measurement, all you need to do just take the square root and then add all the coefficients squared together. Okay, so here we learn a very important thing is to how to normalize the wave function after partial measurement or full measurement. Okay, any questions? Okay, if no, you will see that everything is just very intuitive and straightforward, right? If you think of it carefully, we just give you the theory and math for you to able to handle it or program it. Okay, and everything should make sense. So last week, right, you watched the video. So I want to review a little bit. Now we are at quantum gate. NOT gate is for how many qubits when I write here? Right, in this way. Yeah, it's for 1 qubit in this case. I want to remind you what is the meaning, how we define the function of a gate. We define it by how it changed the basis state. So don't worry about superposition, right? Just think about if I give you 0, what will happen to 0? Well, I give you 1, what will happen to 1? NOT gate is to convert 0 to 1 and 1 to 0, right? And if we write in matrix form, it will be something like this. Because, for example, 0, 1 times 1, 0 times 1, 0, what is this state? 1, 0. 0 will give me, just do matrix multiplication. 0, 1 times 1, so 0 times 1 plus 1 times 0, give me 0, right? 1 times 1 plus 0 times 0, give me 1. This one give me the state 1, right? So we have a way to construct this. We actually talked about that earlier, but for this, you can see that it just fits. Now, once you define how it operates on different bases, the rest is just superposition, right? So now instead of just 0, 1, you can have alpha, beta. Then if you operate on this, if I have a state that is alpha 0 plus beta 1, you get beta 0 plus alpha 1. Looks like you swap the coefficient. So sometimes quantum computing is so simple that you feel, oh, do I really understand it correctly? But it is that simple. Right? If you don't do superposition, it's just the same as a classical gate. Although you are going to see a superposition gate later. And if we go to a higher dimension, right? I want to have a NOT gate for 2 qubit. And we have learned about how to construct the matrix of 2 operator using tensor product. Right? I have 2 qubit and then I go to a larger space. So I will use tensor product. Again, follow the step carefully, right? This will happen in the midterm, right? I give you a quantum circuit, a large quantum circuit. How do you create the whole gate for that circuit? Right? So how do you do tensor product? Just write them in this way and just move each of the block into it, and then do multiplication. Then you will get something like this. And then you will find that if I have alpha, beta, gamma, delta, the output will be delta, gamma, beta, alpha. Right? Basically, it just swap the coefficients. Any questions for this 2 qubit gate? So we learn about NOT gates, then we go to something called control NOT gate. This is a very critical gate. Is something called entanglement gate. Because we need gates like this to perform entanglement. Again, I mentioned at the very beginning, if you don't have entanglement gates in your circuit is not going to be useful because it can simulate or emulate efficiently using classical circuit. So everything can be done by classical circuit, will not give you any advantage, quantum advantage, right? So you do need the entanglement gate. And this is the entanglement gate. There are many things we can review and learn from here. First of all, we define how it is property, again, by the basis state. Here we write A, B. So what are the possible value of A and B? Thank you. 0 or 1. So it becomes 0, 0, 0, 1, 1, 0, 1, 1. We only have 4 basis states. So I only need to define how this 4 basis state will change when I apply this control NOT gate. then I define the CNOT gate. Okay? And this is the definition. It is given. Don't worry, it is given. Right? Someone define it. You can define your own quantum gates if you come up with something useful. So what does it mean? It means the first qubit, whatever what you have, don't change it. Keep it as it is. A is still A. But the second qubit becomes A exclusive OR B. Okay? So what is the meaning of exclusive OR? If you forgot, it basically is saying that if you have both of them are same, 1, 1 and 0, 0, you get 0. If they are different, you get 1. Or this is also equivalent to counting the number of 1. If it is even, then you get 0. If it is odd, you get 1. Okay? We will see that. For example, you apply control NOT gate, and that's why we also call it exclusive OR gate. 0, 0. First of all, the first qubit doesn't change, 0. But the second qubit becomes A exclusive or B, so it's 0 exclusive or 0. Again, how many 1 do we have here? 0, right? So that's why you get 0. So the result is 0, 0. Are you okay with this? Any questions? And similarly for 0, 1. First qubit doesn't change. Don't touch it. That is the definition. Second qubit becomes A exclusive or B. Here is 0 exclusive or 1. Again, but based on the definition of exclusive OR, I have 1, 1, so it becomes 1. So this becomes 0, 1. Right? So you see that it does nothing to the state when the first qubit is 0. So 0, 0 still 0, 0, 0, 1 still 0, 1. But what if it is 1, 0? First qubit doesn't change, still 1. But second qubit is A exclusive or B. Here is 1, 1, so it becomes 1, right? So this becomes 1, 1, because 1 exclusive or 0 is 1. So it changed 1, 0 to 1, 1. It rotates the basis state from 1, 0 to 1, 1. And similarly, 1, 1 to 1, 0. Any question? This is very important. If you cannot understand what I'm talking about, then you cannot appreciate more complicated gates. Yeah.
Yes, I want to ask is how does it relate to the entanglement?
How does it relate to entanglement? Very good. Because if you can add a Hadamard gate in front of it and then apply this gate, then you will create an entangled state. And we will see that very soon. Okay, I'm not showing it here. Yeah, you create a state that has entanglement. Yeah. Yeah.
What LSD means?
Oh, I will talk about this. Yes. Yeah. Good question. One exclusive of 1. Yeah. Oh, that's a typo. Thank you. So it is typo in my book also. Good. Thanks for catching that. So you understand how it works now. Thank you. Right? You understand his question and my mistake? Yeah. 1 exclusive of 1, it should be 0. And you can come up with this matrix, right? Now, someone asked about LSB and MSB. So we have something called little endians, right? It's an Intel convention. You write this register, just classical one. In this case, is something we call little endian. So the one on the right is the LSB, which means the least significant figure. I think you probably understand what it means, right? It's just like 98. 8 is the least significant figure, right? Because it's times 1. 9 times 10, right? 90 is 9 times 10. Those on the left is most significant. Those on the right is least significant. This is called little endians, right? How you store the number in register. There's something called big endians. The one on the right is more significant. But we don't talk about this here. This is the first thing, right? So this one is the MSB. This is the most significant figures, right? So you can have many figures. The far left one is the most, the far right one is the least. Make sense? MSB and LSB. Now, but then we need to draw it in a quantum circuit. This creates a lot of confusion depending on which tool you use and what paper you're reading. So you need to be very careful. In IBM, also in my book, I follow that convention. When you draw the circuits, the bottom one is the MSB. The top one is the LSB. So now let's come back to here. I mentioned in the last lecture, but did not mention here. You see that A doesn't change. We call it the control qubit. B is changed based on the value of A, and that is the target qubit. Is this okay? So A in this case is the in this case MSB is the control qubit, and the LSB is the target qubit. Make sense? Now, so what we are doing here is that when I draw the circuit in here, I deliberately we make the MSB at the bottom. So this is the control qubit. The one on top is the target qubit. And that's why this symbol, this is the CNOT gate, right? The control is at the bottom and the target is at top. It means that if this is 1, then apply this NOT gate. This is just the NOT gate. Look at this. Oh, I use different symbol. But this is just the NOT gate. Some people just make it cross X. Okay? So we learn a few things. What is LSB and MSB? It's just about which one is more significant. And we need to have a unified system when you write the paper or you write the program. Which one is MSB, which is LSB, right? And then when you draw the circuit, you can draw it in this way also if I want to. If I make it clear this is MSB, this is LSB, I just need to make sure that I swap the circuit. This is equivalent. Is that okay? Right? The only difference is just this one I stand upside down, and I stand up, and this one I do stand upside down to look at it. The circuit doesn't change. Still, MSB control the LSB. Right? Of course, you can also have LSB control MSB. That is also okay. Then your matrix will be completely different. Right? So you need to be very careful about this. We will look at this later when we look at swap gates, etc. How to implement a swap gate by using control NOT gate. But is that okay? Do I answer all your questions? Okay, so this is CNOT gate. Then we talk about swap gate also. Now you should be very comfortable when you see swapping AB to BA. Yes, you have a question? Okay, swapping AB to BA. What does it mean? Again, A and B can take the values, a value from 0 and 1. Okay, so it can be 0, 0, 0, 1, 1, 0, 1, 1. And we define swap gate by defining how it changed the basis state. And swap gate say that, just swap them. So if 0, 0 is 0, 0. 0, 1 becomes 1, 0 because you swap them. Okay? 1, 0 becomes 0, 1, and 1, 1 becomes 1, 1. And this is the matrix that you have. And you definitely can see that, and this is the symbol. There are different symbols. That's one of them. Alpha 0, 0 will not change. Delta 1, 1 will not change. But 0, 1 become 1, 0, so the gamma 1, 0 become beta 1, 0, right? You swap the state just like swapping the coefficient. And that is the swap gate. This is also a 2-qubit gate, but it's not an entanglement gate because you cannot use it to create any entangled state, which we'll discuss later. What is the meaning of entangled state? Okay, swap gate. And then now we will have something new. I want to talk about the 1-bit phase shift gate. So again, we follow what I just said. This is very important. I hope you can remember this forever. To define the gate, we define by saying that, for example, I apply the phase shift gate, and it has a parameter called phi. right? Apply it to 0, it is 0. That is just the definition, okay? I gave the definition because it turned out to be useful, right? Someone defined it, of course. And when this gate is applied to 1, it becomes e to the power I phi 1. So it is still 1. The basis state is still 1. But you add an additional phase in front of it, e to the power I phi. That's it. And if you forgot, e to the power I phi equal to cosine phi plus I sine phi, right? The Euler formula, right? And so what is the magnitude of e to the power I phi?
What?
Equals to 1 because it's just cosine phi squared plus sine phi squared, right? Equal to 1. And that's why this is important, because remember, for all the probability we have talked about, it's related to the square of the magnitude of the coefficient. If you add this e to the power I phi to the coefficient, are you going to change the measurement probability? No, right? Because its magnitude is 1. You only change the phase, right? And but if this is a so-called global phase, let's say this e to the I phi is applied to every coefficient, then you really don't care. It has no physical significance. But this one, when you apply the gate, it only applies to the one part. So there's a relative phase change between 0 and 1. Although their corresponding magnitude square are still the same. But this is going to have some implication if you continue to do some quantum computing. Okay? So that is the definition. So if this is the definition, then I can tell you that the matrix form is just equals to U phi U phase shift phi equal to 1, 0, 0 e to the power I phi. Okay. Now you can check it. You find that it works. But maybe now I want to introduce a way that you actually know that. Do you remember how to construct the elements of a matrix? I think you probably forgot, right? The elements of matrix, Mij, the elements, right? The ith row, jth column. We learned that in the last few lecture. I forgot which lecture. Yeah, something like the inner product, right? Is the basis state I, M, J. Do you remember this? Okay. So, for example, I want to know what is UPS phi 1, 1. It is equal to 1 UPS phi 1, right? But what is UPS phi 1? By definition, right? It's just equal to e to the I phi 1. And e to the I phi is just a number. I can take it out, and it's orthonormal. So this is just equal to e to the power I phi. Correct? And that is how I can construct this matrix if I really want. If I don't know how to find the element, I can do it in this way, right? Or we can already see this because this is simple enough. So in principle, you try to construct all the matrix by using all the elements by using this method. Yeah, questions? I don't have a physical picture. So now you are saying that it's a superposition of spin up and spin down. But that superposition already have some phase difference because you have alpha 0 plus beta 1, right? And what you do is just further shift beta by e to the power I phi, right? So you add an additional phase. So if it's still the qubit by itself, there is almost no physical significance because when you measure, the probability of getting 0 and 1 up and down are still the same. because e to the power I5 has a magnitude of 1, right? But if you use this to do further operation or to have interference with another qubit, for example, then this one can cause some constructive or destructive interference. Then it will have a physical significance. Yeah. So there's a phase shift which we cannot observe in classical world. Yeah. Unless we do some interference. Okay, this is good. Now, with this, let's look at some special cases. If phi equal to pi, what is this matrix? First of all, what is the e to the power I pi? Is equal to cosine pi plus I sine pi. What is this? -1. Thank you. Yeah, if you forgot, just check table, ask ChatGPT. -1, right? So the matrix becomes UPS, I'm not advertising, 1 equals 0, 0, 0, -1. What is this? Sigma C. So sigma C is a special case of phase shift gate with the angle equals to pi. Okay, then you imagine I can have other angles, and indeed later you will see S gate, T gate, which is just have the pi equal to pi divided by 2 and pi divided by 4. Okay, and these will construct the universal set of quantum gates with Hadamard gates and other gates and entanglement gates. Okay, this is one thing. Now I also want to show you another thing. Now, if I apply sigma C to the plus state, what would it be? Difficult to see, right? But let's take a look. What is, okay, you are very fast. He said it's minus. What is plus? What is plus state? 1 over square root 2, 0. I need to make it into a matrix form, sorry. Zero plus so maybe I will just say, let me still spell it out. But plus state is just superposition between 0 and 1 state, right? 1, 0 and 0, 1. Everyone okay with what I'm writing here? Any questions? Why this is plus state? It's a superposition of the bases. I put in this is 0, this is 1, right? 0 cat, 1 cat. That's what I mean. Okay, so you apply this to it. What do you get? You do a multiplication, right? So 0 times this equal to 1, and this is, right? So this you will get 1, 0, nothing changed. But then the next one becomes -0, 1, because I have a negative here, right? Because 1 times 0 plus 0 times 1 is 0. 0 times 0, -1 times -1 is -1, right? So this is equal to a minus state. So what I'm trying to say is, you apply sigma C to the plus state, it becomes the minus state. If I were in the eigenstate basis of sigma x, which has the plus and minus as the basis state, then what is a sigma C gate? You see, sigma C gate is just a NOT gate in the plus minus basis. That is just what I want to show you. Sigma C is a phase shift gate in our 0-1 basis. But if I try to look it in the plus minus basis, it's actually a NOT gate. Make sense? Okay. So we have 1 qubit gate. Again, it's just math, right? You just need to go through it. The main point is that how you define a gate. Now, naturally, I want to know about something called 2 qubit phase shift gate. But this is not a simple one because it's not just a tensor product of two 1 qubit phase shift gates, because that becomes not very interesting. What we're talking about is something called control phase shift gate. Now, based on this name, control phase shift, and what we learned earlier, control NOT, can someone try to guess what does it mean by control phase shift? I mean, what is the intention based on what we discussed in control NOT? See? Very good. First, let's don't call it whether the first qubit or the control qubit doesn't change. And what happened to the second qubit if we call it this way? You will have a phase shift for the second qubit, but will it always get the phase shift? Based on what we learned in control NOT.
If only the control bit is 1.
Thank you. Yeah, very good. So you combine together. Just like control NOT gate, you have 2 qubits. Control, the one who is controlling you is not going to get shift. The second qubit will get shift if the control qubit is 1, right? Just like in control NOT, the second qubit doesn't change unless the control qubit is 1, then you apply the NOT gate to it. So let's see if this is the case, because we are just guessing, right? So the definition is this, and we can check if that is correct. Now we try to make it more compact. Control phase shift phi, then you know that phi is a parameter, applied to AB equals to e to the power I A dot B. This is much more than what you expected, right? Phi AB. So does this agree with what you just said? If the control qubit is 0, do nothing. If the control qubit is 1, apply phase shift to the second qubit. We don't know yet, right? Maybe some already see it, but let's check. Right? So if I apply the control phase shift gate phi to 0, 0, what happened? Based on this equation, it is, I no need to use arrow, I just equals to e to the power I, what is that? 0, because 0 dot 0, 0 times 0, okay? Phi, 0, 0. What is e to the power 0? 1. So this is equal to 0, 0. Make sense? This is the definition. I'm trying to check it on every basis state. I start with 0, 0. I get 0, 0. And you probably, based on what you just saw, you probably already know that control phase shift phi applied to 0, 1, what is it going to give you? Huh? It's going to give you something like this, right? So this is 0, 1. Then what will be here? 0, 1. It won't change, right? But then the exponential is what? 1. Yeah, the whole thing is 1 because it's 0 times 1, right? E to the power 0 times 1, right? So as long as you have a 0 in A or B, this guy is going to give you 1, right? So no change. So naturally, I also expect that one 0 equals to e to the power I 1.05. 1, 0 is going to give me 1, 0. Right? Now, what if it is 1, 1? This is e to the power I 1 times 1, 5, 1, 1. correct? And what is this? E to the power I phi 1, 1. Right? So is this okay first for the math? Make sense? Now let's check what we just said. We expect a control phase shift gate behave in this way. If the control qubit, although I did not say what it is, we kind of assume this is the control. The first one is control. The second one is the target qubit. First of all, as you just said, the control qubit is not going to change, no matter what. 0 still 0, 0 still 0, 1 still 1, 1 still 1, right? And the target qubit is what? If the control qubit is 0, do not do anything. Control qubit is 0, then do nothing. So 0, 0 is still 0, 0. 0, 1 is still 0, 1, right? But if the control qubit is 1, then apply the phase shift gate to the second qubit. What is a phase shift gate? Phase shift gate is that you do nothing to it if it is 0. You apply e to the power I phi if it is 1, right? So here, control qubit is 1 phi. So I'm going to apply a phase shift gate to the second qubit. But the second qubit is 0. So I again do nothing. So it is still 1, 0. But for this one, control qubit is 1. So I'm going to apply a phase shift gate to the second qubit. And the second qubit is 1. So I need to multiply it by e to the power I phi. And that's why I get this. And I hope that you are okay to see that this one is the same as e to the power I phi 1 tensor product 1, which is the same as 1 tensor product e to the power I phi 1. Do you see that? And that is exactly what we are saying. If the first qubit, control qubit is 1, apply phase shift gate. And the phase shift gate is what? Apply e to the I phi if this is 1. Or apply 1 if this is 0. Right? So any questions? Yeah. Sorry. Now this one is really confusing. I should have emphasized it. When I say A dot B, you can think of A times B or A and B. Usually it's actually A and B. Depends on the context. And it's the AND operation. Okay, so that is not a matrix. When I have this A dot B, it means A times B. So if this is 0 times 0, 0 times 1, 1 times 0, 1 times 1. Okay? And this is actually, to be more precise, it's just A times B modulus 2. But for now, just treat it as multiplication. No, not modulus 2. I mean, it's meaningless because it's multiplication. Let me don't talk about this. Later, you will see another inner product, etc. Okay, so that is control phase shift gate. Okay, so in summary, right? So therefore, this control phase shift gate is apply phase shift gate if the control is 1. That is the summary of what we have done so far. Okay. Then what is the matrix form? Matrix form is also easy. You can construct based on what we have discussed earlier, and it is given as 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0 and then 0 0 0 e to the power I phi. Right? Any questions? Really fast today. Okay, if no questions, then let's go to the last simple gates that we will learn. Did I do something wrong? Okay, so I'm sorry. This this one should be in the previous page. I don't know what I did. This is for the previous slide. This is the circuit for control phase shift gate. Okay, I did not, I make a mistake when I paste it. It should be go to the previous slide. So again, your MSB is here. This is the control node. And this is the target. Okay, so if your control is 1, then you apply phase shift gauge to the second qubit. And that will be the equation. It doesn't change anything, only add the phase in front of 1, 1. Okay, so I messed up the slides. So now I have another topic is about the Toffoli gate. Somehow do I spell it correctly? Anyone know?
Yes.
Okay, somehow I deleted the title. Let's talk about Toffoli gate. Okay, so it's a 3 qubit gate. And again, how do we define a gate? Whenever you invent something, right? How do you define a gate again, a quantum gate? You matrix, but matrix that is great, yeah. But behind that is like how does the gate transform every basis state? Yeah, you always need to have the same number of input equal to number of output. But I mean, you define a gate by defining how it transforms every basis state. Okay? So now it's a 3 qubit gate. How many basis states do you have? 8, thank you. So a general 3 qubit gate, a general 3 qubit basis state, right? You can have A, B, C, with A, B, C taking the value of 0 of 1. So it can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, right? 1, 2, 3, 4, 5, 6, 7, 8. And of course, remember, we can also write them as 0, 1, 2, 3, all the way to 7, right? If you want to write it. But now we are playing with this qubit gate. Of course, we need to be very clear about what it is. So, Toffoli gate, we call it T. This is the definition. T applied to A, B, C is going to give me A, B, and then A dot B exclusive or C. Okay, so looks very complicated, but no, you just be very careful. Calm down, think about what it's talking about. Yes, 3 qubit. Again, A, B, C can take any 0 and 1. After that, as you said, we still have 3 qubit, right? So A is still A, B is still B, but the last one becomes C exclusive or A and B, or A times B. Then let's just review some terms. First of all, which one is the MSB? Which one is the most significant bit in our class? A, thank you. This is the MSB. Which one is the LSB? Thank you. Right? Left is the MSB, right is the LSB. So then based on this, can you guess which one is the target qubit? Which one is being controlled? C. So this is the target. Which one is the control qubit? Right, A and B. Because all of you see that the result of this qubit depends on A and B, right? Very good. So actually you have two control qubit, A, B, they are the control qubit. So based on this, you see A times B, right? So let me just tell you something, maybe you don't know, you forgot. If 0 exclusive or something, what do you get? 0 exclusive or something. It actually gives you the same thing, right? Because if you C is 0, 0 exclusive of 0 is 0. If C is 1, C exclusive 1 equal to 1, because you're counting the number, right? How about 1 exclusive or something? If C is 0, 1 exclusive of 0 is equal to 1, right? And then if C is 1, 1 exclusive 1 is 0. So like what he said, equal to not C. I hope you, if you're not familiar with this, then this is the not symbol. Yeah. Apply what without measurement? Okay. Although the way I say is like if A and B are, let's don't talk about Toffoli gate, just talk about it. Although the way I describe it, I think that CNOT gate is just like if the first gate is 1, you apply the NOT. If not, you don't apply the NOT. But this is just the way we're thinking, how we think. Okay, we don't need to do measurement. It just naturally, this is the action of the gate, that's it. So there's no measurement. It's not saying that, oh, I see the first bit is 1, then I'm going to apply the NOT gate. Do I answer your question? No. Let me think about, you know what is AND gate, right? Yeah. 0, if one of them is 0, right? If 0, 0 give you 0, 0, 1, 1, 0 give you 0, 1, 1 give you 1, right? That's AND gate, right? But I can explain this to a student in this way. AND gate is that if you have a 0, your output is 0. If both are 1, your output is 1. Do you need to do any measurement for AND gate? It's just the way I express it. I just say that, okay, AND gate is just like that. If any one of them is 0, your output is 0. If both are 1, then it is 1. But still, it's just the gate. You input something, it gives you the result. That is, make sense? So when I say CNOT gate, I try to explain to you, it's just help you to understand the meaning of the gate. But the gate, you don't need to do any measurement. Yeah, question? So same for Toffoli gate. Cycle time, right? So you mean how long does it take to complete the the gate operation, right? Yeah. So in classical logic, you need to wait for a signal to propagate. That is the delay time of a gate, right? For example, NOT gates, you have low to high rises in the input, and then look at the output, how long it takes from high to low, then 50 to 50, whatever, right? That is the delay time. What is a quantum gate? We did not discuss in this class because we don't have hardware, but I kind of briefly say that it's just a microwave pulse or laser pulse. And what you want to do is to let the quantum state to evolve from one state to another state. And now it becomes the Schrodinger equation, right? Under that Hamiltonian, then it would take times to change one state to another state. And that will be the time of the gate. And there is another constraint is that you apply a pulse as long as it is not infinitely long, you don't have a well-defined frequency. So So if you have a short pulse, you might have some higher frequency if you do Fourier transformation. And that can cause your qubit to fail because it can be excited from one state to another state outside of the Hilbert space. And so you need to have a certain width to reduce the infidelity. And that also limits your gate time. And that is the so-called gate time. For example, in superconducting qubits, it may be around 200 nanoseconds to do a NOT gate in a typical qubit. Yeah. 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 Exactly. Mm-hmm. Yeah. Yeah. Very good. So I just gave an example on superconducting qubit, exactly like what you said for different architecture. If it's trapped ion, photons, they have different gate time because they just have different physics. Okay. So go back to this. I just want to make it clear. The way I say it is not how it really operates. When I say when A and B are one, then what happened? This is just the way to understand it. The gates will just do it as it is. So we just introduced this one exclusive or something is just the NOT gate. So then you will boil down to C is not going to change if A times B is 0, right? Because 0 exclusive with C is always C. So what I'm trying to say, this is equals to A, B, C if A times B equal to 0. Or it is equal to AB not C if AB equal to 1. Make sense? Now so quantum computing is easy in some sense. You even just look at all this. Which state is going to change? You're just trying to say which state has A times B equal to 1. 0, 0, no. As long as you have a 0 in front of at the first 2 qubits, A times B is always 0. So these 6 states are not going to change. Only the last state is going to change. And you change it by negating the last qubit. So you will change from 110 to 111 or 111 to 110. Make sense? This looks like what kind of action? Change 0 to 1 and 1 to 0. I mean, change 1 to 0 and 0 to 1. What type of gate is that? NOT gate. But when would it change? When A and B, when control bit. So we have 2 controls. So what do you call it? Very good. So this is also called, so let me say, so only apply NOT to C if A equal to B equal to 1. So this is also called control NOT. And you can imagine, I can also have control NOT. And indeed, right, we do have algorithm using this, right? But you are not going to imprint one gate because the infidelity is very low, very high, very bad, lots of noise, right? You are going to break these gates into many smaller gates, and they can be formed by many 2 qubit control NOT gates and some 1 qubit gate. Okay, but this is good to learn about this concept. So finally, what is the matrix? Because it doesn't change anything, right? And I'm lazy, I'll just write the diagonal. 1, 1, 1, 1, 1, 1. The first 6 doesn't change. And then last one, it will change just like the NOT gate. And then the rest is 0. Is this okay? And we can check again, use what we learned earlier about how to construct a matrix. For example, can you tell me what is T77? This is just an example. What is T77? How do you find T77 if you don't have the matrix given? Which equation again? This equation? Right, so how do we write it? T77? 7 bra T 7. Yeah, a little bit confusing, 7, right? But what is 7? 1, 1, 1, right? But what is T applies to 7 based on what we have learned? 1, 1, 1. 1, 1, 1. T applied to 7 is what? Equals to 1, 1, 1 times 1, exclusive or 1. I know this is long, but you just follow it. Because this is A. T applied to 7. 7 is 1, 1, 1. So A is 1, B is 1, C is 1. So A is 1, B is 1, C is A times B exclusive C. So it's 1 times 1 exclusive or 1. I know it's long, but if you follow it, you understand it, then this is understandable, right? So what is 1 exclusive or 1? 0. So this become 1, 1, 1 inner product with 1, 1, 0. What is the inner product between 1, 1, 1 and 1, 1, 0? 0. Because they are orthogonal, right? So maybe some of you don't feel that comfortable with this. We can further change it to this. This is just tensor product. Oh. I need to intrude into this space. This is just 1 tensor product 1 tensor product 1, and then we try to have inner product with 1 tensor product 1 tensor product 1, right? Am I right? Are you okay with this? But remember, this is just different space. This is what the first qubit. This is the second qubit. This is the third qubit. So when you do inner product, you do them individually, right? You don't cross the space. The first qubit need to inner product with its own qubit. And the last one should be 0, not 1, sorry. Correct? And this is equals to 1 inner product 1 for the first qubit. What is the 1 inner product 1? 1. 1 inner product 1 for the second qubit is what? 1. The last qubit is 1 inner product 0. This is 2, this is 3. What is that? So it's 1 times 1 times 0. That's why this is 0, right? And this 0 is this 0. That's how you get the matrix element. You don't need to do this. You think too detailed or stupid thing. You should just trivial to me. They are just 2 different bases. They are orthogonal, right? But if you